ያው መቆራረጥ ነው እየተቆራረጠ ያስቸግር ነው ምኑ ስለሚጠፋ Okay, good morning to you. In our discussion the previous week, we have seen the two most important theorems that are used to find the rational zeros of a polynomial, which is called the rational zero of a polynomial, and the other theorem, location theorem, which is used to locate the irrational zeros of a polynomial between consecutive integers. Today we are going to see how we can sketch the graph of a polynomial function. As you all know, sketching the graph of a function is a process, and this process involves different steps. From among the most common steps involved in sketching the graph of a function are determining its x-intercept, determining its y-intercept, and particularly for a function like a polynomial, maybe there is a need to construct a sign chart to see where the given function is, its graph lays below the x-axis, where its graph lays above the x-axis. That means where f of x is negative, where f of x is positive, and this kind of information is obtained from the sign chart we construct, for example, B and D. First, let us begin our today's discussion with this example. That is f of x is equal to minus x squared minus 2x plus 8. Actually, you have learned about the graph of this degree 2 polynomial in grade 9. It is called a parabola. So to sketch the graph of a parabola, we need to undertake 4 steps. These 4 steps are determining its x-intercept, its y-intercept, the vertex, and determining the nature of the parabola. So determining the x-intercept is simply solving f of x is equal to 0. So f of x is equal to 0 in this case is minus x squared minus 2x plus 8 is equal to 0. So you can choose between the general quadratic formula or the factorization method to find if there are any zeros for this polynomial f of x. Minus x squared minus 2x plus 8 is equal to 0. Now, if you try to solve this with the factorization method, you need to find 2 integers. Their product is minus 8 and their sum is minus 2. Find 2 integers. Their product is minus 8 and their sum is minus 2. If these integers exist, they are from the factors of 8. From the factors of 8, from the factors of 8, 2 of the factors of 8 that satisfies this condition. Their product is minus 8 and their sum is minus 2. They are minus 4 and positive 2. So 2x minus 4x plus 8. Now, the number of terms in this quadratic equation is 4. So by taking 2 at a time and factorize, it results in the following: minus x, which is the GCF of these 2, into x minus 2. And the GCF of these 2 is minus 4 into x minus 2. So x minus 2 is common. X minus 2 times minus x minus 4. It is the factorized form of f of x. Now, if you take again minus x out, then you have minus negative x minus 2 times x plus 4 equal to 0. So the zeros of this polynomial using the zero product property is x minus 2 equal to 0. The value of x is equal to 2. x plus 4 equal to 0, the value of x is equal to minus 4. So at these 2 points, 2, 0 and minus 4, 0, f of x or its graph crosses the x-axis. So the first step, we are done. So we have to pass to the next step, that is determining the y-intercept. So there is no need of making any calculation when we are determining the y-intercept in sketching the graph of a polynomial, because for a polynomial, it is constant term, or the constant term is the point where its graph crosses the y-axis. So 0, the constant term, that is 8. It is the y-intercept of the graph of f. Then the next step is determining the vertex. So to determine the vertex, first identify a, b, and c. A is the coefficient of x squared, it is equal to minus 1. B is the coefficient of x, it is equal to minus 2. And c is the constant term, that is 8 in this case. Now, after identifying the values of a, b, and c, then the vertex is simply obtained from this formula. Its first component is minus b over 2a, and its second component is 4ac minus b squared over 4a. So after substituting a, b, and c in these formulas and simplifying, results in the first component of the vertex is minus 1, its second component is 9. Then the last step is nature of the parabola. The nature of the parabola is determined by observing the sign of the leading coefficient. If the sign of the leading coefficient, that is the coefficient of x squared, is a positive number, the parabola is an upward parabola. And if the coefficient of the leading term, in this case, the coefficient of x squared is a negative number, the nature of the parabola is a downward parabola. So because the coefficient of x squared in this case is minus 1, the nature of the parabola is downward. So first, locate these 4 points in the xy coordinate plane. The 2 points where the graph of f of x crosses the x-axis, the point where its graph crosses the y-axis, and the vertex. So after locating these points, you simply join these points by a downward parabola, and that is the graph of f of x. And it looks like this one. It crosses the x-axis at minus 4 and 2. It crosses the y-axis at 8, and its vertex is at minus 1, 9. Exactly, the graph of f of x is this one. This is the graph of f of x, a downward parabola which crosses the x-axis at minus 4 and 2. It crosses the y-axis at 8, and its vertex is minus 1, 9. From your grade 9 mathematics lesson, I hope you remember that the vertical line that passes through minus 1 is the line of symmetry, and the range of this function is y less than or equal to the second component of the vertex, that is 9, and the other thing is the maximum value on the graph of f is this point, that is 9. 9 is the maximum value of this function. If it was an upward parabola, the second component of the vertex will be taken as the minimum value of this, and its range, as you remember, is y greater than or equal to the second component of the vertex. Now, let us pass it to the next example, the second example. P of x is equal to 3x cubed plus 4x squared minus x minus 2. Now, the first step in sketching the graph of this polynomial is determining its x-intercept. Determining its x-intercept is simple. It involves simply solving the equation P of x is equal to 0. P of x is equal to 0 means 3x cubed plus 4x squared minus x minus 2 equal to 0. Now, by using the rational root test theorem, that means by listing the factors of the constant term 2 and the factors of the leading coefficient 3, then the possible rational zeros of this polynomial are the list of factors of 2 over 3 in its simplest form. Then from among those list of possible zeros of this polynomial, the only rational zeros of the polynomial are 2 over 3 and minus 1. So if you write f of x, I mean p of x in its factorized form, it is equal to 3x minus 2 times x plus 1 the whole square. Now in this case, these two numbers, x plus 1 the whole square, the power or exponent of the factor x plus 1, and 1, which is the exponent or the factor of 3x minus 2. They have an effect on the shape of the graph of p of x. We call it these numbers multiplicity of the factors. So in graphing a polynomial, the multiplicity of a factor or the multiplicity of a 0, that means, is that the multiplicity or the number, is it even or odd? Does have a direct effect on the shape of the graph. For example, x plus 1. That means x is equal to minus 1. Its multiplicity is an even number, means at x is equal to minus 1, the graph of this polynomial touches the x-axis without crossing the x-axis. But at x is equal to 2 over 3 and similar factors, it crosses the x-axis from above to below or from below to above. It depends on the sign chart or from the information we obtained from the sign chart. Then at x is equal to 2 over 3, the graph of p of x may cross the x-axis from below to above or from above to below. So x is equal to 2 over 3 or x is equal to minus 1 or minus 1 comma 0 and 2 over 3 comma 0 are the x-intercepts of p, not f actually, p. The y-intercept is simply you make the first component of this point 0 and you take the constant term. So 0 comma minus 2 is the y-intercept of the graph of p. Now, to see the sign of p of x in different intervals, construct a sign chart as follows. Please very carefully watch how the sign chart or this table is constructed. First, we consider the numbers that makes this polynomial equal to 0, and by keeping their order, we locate them on a number line as follows. Because minus 1 is less than 2 over 3, so you write minus 1 to the left of 2 over 3, and always when you are constructing the sign chart, left extreme is negative infinity, right extreme is positive infinity. Then you write the factors of p of x, 3x minus 2, x plus 1, because the sign of x plus 1 the whole square can be determined from the sign of x plus 1. So if there is any factor in the factorized form of a given polynomial, if its multiplicity is greater than 1, therefore you have to write first the factor whose exponent is 1, then you can determine the sign of that factor whose multiplicity is greater than 1. For example, x plus 1 the whole square. So after writing x plus 1, based on its sign, you can determine x plus 1 the whole square. Finally, the polynomial is the product of 3x minus 2 and x plus 1 the whole square. So this table has 1, 2, 3, and 4 rows. But our interest is on the last row of this table. So before coming to see or read the last row of this table, 3x minus 2 at x is equal to 2 over 3 is 0. And what is the sign of 3x minus 2 for values less than 2 over 3? For example, if you substitute x by minus 1 in 3x minus 2, what is the sign of 3x minus 2? 3 times minus 1 is minus 3. Minus 3 minus 2 is minus 5. That means for values less than 2 over 3, the sign of 3x minus 2 is negative. So negative, negative, and for values greater than 2 over 3, simply take an integer that is greater than 2 over 3 and evaluate 3x minus 2. If you make this evaluation correctly, then if the sign is negative, then the sign of 3x minus 2 remains positive. For example, if 3x minus 2 is positive in this interval, so for this particular case, let us take 1, because 1 is greater than 2 over 3. So 3 times 1 is 3. 3 minus 2 is positive 1. That means for values greater than 2 over 3, the sign of 3x minus 2 is positive. Now we determine the sign of 3x minus 2. We pass to the next factor, x plus 1. X plus 1, it is equal to 0 when x is equal to minus 1. Now what happens to the sign of x plus 1 for values less than minus 1? Again, In this case, you will take integers less than -2 and substitute in this expression x by that selected integer. For example, if you take -2 is less than -1, so -2 plus 1 is -1. The implication of this is x plus 1 remains negative in the interval -1 up to negative infinity. So x plus 1 is negative. And what happens to the sign of x plus 1 for values greater than -1? You can take 2 over 3 as an example. 2 over 3 plus 1, it is 5 over 3. 5 over 3 is a positive number. That means for values greater than -1, x plus 1 is positive. Now x plus 1 the whole square, its sign can be determined from x plus 1. Take the sign of x plus 1 and square it. Negative square is positive because negative times negative is positive. 0 square is 0. Positive square is positive. So x plus 1 the whole square is everywhere positive except at x is equal to -1. Because at x is equal to -1, it is equal to 0. But for values different from -1, it is positive. Now 3x minus 2 times x plus 1 the whole square of p of x. So to determine the sign of this, take the product of the sign of 3x minus 2 and x plus 1 the whole square. 3x minus 2, for values less than -1, it is negative. And x plus 1 the whole square is positive. Now what is the product of a negative quantity and a positive quantity? I am not asking you the magnitude, simply the sign. So a negative quantity times a positive quantity is always negative. At x is equal to -1, already it is identified, and p of x is 0. At x is equal to 2 over 3, it is 0. Then between -1 and 2 over 3, because 3x minus 2 is negative and x plus 1 the whole square is positive, the product of negative and positive is negative. And finally, in the interval 2 over 3 up to positive infinity, the sign of 3x minus 2 is positive, the sign of x plus 1 the whole square is positive, and the product of positive and positive is positive. Now we totally ignore the 3 rows of this table and we focus on the last row. As you can see, p of x is equal to 3x minus 2 times x plus 1 the whole square for values less than -1 is negative. Between -1 and 2 over 3, still it is negative. But remember, it crosses the x-axis at x is equal to -1. Then for values greater than 2 over 3, it is positive. First, locate these 3 points where the graph of this polynomial crosses the x-axis, the y-axis at x is equal to 1 and x is equal to 2 over 3. Because it touches the x-axis, then we locate 1 and 2 over 3, then -2. Because as you can see, the constant term of this polynomial is -2. So it crosses the y-axis 2 units below the origin. Now, the sign chart, sorry. Okay, so sorry for the interruption. Now, earlier I told you that the multiplicity of x plus 1 is an even number, and at x is equal to 1, the graph of this polynomial doesn't cross the x-axis, but it rather touches. Touching and crossing, now you can see from this graph. For values less than -1, the graph of p of x is negative, means it definitely lays below the x-axis. Then at x is equal to -1, at x is equal to -1, it touches the x-axis. Then between -1 and 2 over 3, still the sign of p of x is negative, means its graph lays below the x-axis. So it turns back, but while turning back and becoming negative, you shouldn't remember that the graph of p of x crosses the y-axis at x is equal to -2. So it touches the y-axis at -2, turns back, and goes up, as you can see, between or in the interval 2 over 3 up to positive infinity, the graph of P is positive. So it is positive and crossing the x-axis. So this is the graph of this polynomial P of x is equal to 3x cubed, 4x squared minus x minus 2. And in sketching the graph of a polynomial, you have to always remember that sharp corner is not allowed. The graph of a polynomial is simply a smooth curve, just like this. So these peaks and valleys on the graph of a polynomial, they are called local extremums. Actually, a detailed discussion about local extremum, how we can find the local extremum, is presented for you in grade 12 mathematics. But for as far as grade 10 mathematics lesson is concerned, these peaks and valleys are called local extremum, and local extremum is a maximum or a minimum value of a function in a given interval. And if a function, for example, you can take a degree 2 polynomial, has a minimum or a maximum value, that is the maximum or minimum value throughout its domain, it is called absolute minimum or absolute maximum for the graph. But in most cases, a polynomial, if its degree is greater than 2, then there is no absolute minimum or absolute maximum. Rather, we will have a local extremum, and a local extremum, as I said earlier, is the maximum or minimum value of a function obtained in an interval. For example, the graph of this polynomial P of x has a local maximum at x is equal to minus 1, and it has a local minimum at x is equal to 0, because at this point, it is a point on the y-axis, its first component is 0. So at x is equal to 0, it has a local minima, and at x is equal to minus 1, it has a local maxima. A local maxima is a peak on the graph of a polynomial, and a local minima is a valley on the graph of a given polynomial. So having said this, if you have any question, you can forward it before passing it to the next example. Okay. Let us consider the next example. The next example is again a degree 3 polynomial. F of x is equal to 2x cubed minus 6x squared plus 1. 2x cubed minus 6x squared plus 1. So for this polynomial, the first step to sketch its graph is finding the x-intercept. And to find the x-intercept, solve the equation 2x cubed minus 6x squared plus 1 equal to 0. You can check it for yourself, but this polynomial has no rational 0. A given polynomial has no rational 0 doesn't mean that it has an irrational 0. So if there is always a possibility for a polynomial to have an irrational 0, so you have to think about location theorem. And simply, you have to construct a table of values. And between consecutive integers where the given polynomial changes its sign from positive to negative or from negative to positive, then according to location theorem, this polynomial has at least one irrational 0. So to apply this theorem, let us prepare a table of value for this polynomial. F of x is equal to 2x cubed minus 6x squared plus 1. So the table is Okay, take these 5 integers, 6 integers, -2, -1, 0, 1, 2, and 3 as values of x and evaluate this polynomial f of x. The values of f of x are -39, -7, 1, -3, -7, and 1, when the value of x is respectively -2, -1, 0, 1, 2, and 3. Now, where f of x changes its sign between consecutive integers, there is at least one rational zero. So between -1 and 0, the value of f of x changes from -7 to +1. So there is at least one irrational zero of this polynomial between -1 and 0. Then between 0 and 1, the value of f of x is 1 at x is equal to 0, and its value changes to -3 when f of x is equal to 1. So between 0 and 1, another irrational zero of this polynomial is obtained. Then, if you continue observing the last row of this table, f of x changes its sign between 2 and 3. At x is equal to 2, its value is -7, but this value is changed into +1 when the value of x is 3. Actually, if you continue evaluating f of x at x is equal to 4, 5, 6, 7, etc., the sign of f of x remains positive, so there is no need to waste your time. And in this direction, if you continue evaluating f of x at x is equal to -3, -4, -5, etc., f of x will remain negative, so there is no need to waste our time. Simply, we have to evaluate this polynomial between these 5 integers. The integers from -2 up to 2. If there is a need, we may evaluate the polynomial at 3 and 4 and -3 and -4. It is rarely, but most often, by evaluating the polynomial between -2 and 2, we can determine the irrational zeros of a polynomial. ربش بوجه؟ እኔ አትረብሹኝ። ተረጋጋ በቃ። Okay. Now, there is no need of going through other steps. We simply have to take these values onto the xy coordinate plane, and we can sketch the graph of this polynomial. So we mark a point between -1 and 0 because this polynomial has a zero, an irrational zero between these consecutive integers. And then we mark another point between 0 and 1 since f of x changes its sign. Then between 0 and 1, and finally between 2 and 3. Actually, earlier in our discussion, we have said that the maximum possible number of zeros for a given polynomial is equal to its degree. So this polynomial is a degree-3 polynomial, and it changes its sign between these consecutive integers at 3 different instances. Therefore, we can sketch the graph of this polynomial as a smooth curve. As you can see, for values less than -1, f of x is negative. So between -1 and 0, we mark the point, and then for values less than -1, because it is negative, you can sketch just like this. Then at x is equal to 0, the value of f of x is 1, and it means 1 unit above the origin, the graph of f of x crosses the y-axis. So we mark this point, then it touches x, the y-axis at y is equal to 1, then it turns back between 0 and 1. Again, the graph of this polynomial crosses the x-axis, then it reaches somewhere and it turns back. There is no need to know the exact location of this point where f changes, where this value appears. Rather, we have to focus on the sign of f of x. It remains negative, then between 2 and 3, where the graph of this polynomial crosses the x-axis, then after that it is positive. So this smooth curve where it crosses the x-axis between 2 and 3, between 1 and 0, and between 0 and -1, and at y is equal to 1. By sketching this smooth curve, we sketch the graph of this polynomial. As we have said, at x is equal to 0, this polynomial has a peak, and we call it this a local maxima at x between 1 and 2. We don't know the exact value where this value is appeared, so we can say that between 1 and 2, at x is equal to 1 and x is equal to 2, there is a local minima for the graph of this function. So this is the graph of this polynomial. So the final example for the day, it is again a degree 3 polynomial. G of x is equal to x cubed minus 4x squared plus x plus 6. And this polynomial, because has irrational zeros, there are 3 steps involved before we start sketching the curve representing g of x. So the first step is it is x-intercept, and it is x-intercept is obtained by solving the equation x cubed minus 4x squared plus x plus 6 equal to 0. So x cubed minus 4x squared plus x plus 6 equal to 0. The leading coefficient of this polynomial is 1. So using the rational root test theorem, list the factors of 6. Then from among the list of factors of 6, the possible rational zeros of this polynomial g of x will be obtained. So the possible list of factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So by the rational root test theorem, if this polynomial has any rational zero, it must be among from the 8 numbers I already mentioned, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 6. So from among this list of possible rational zeros, minus 1, 2, and 3 makes this polynomial equal to 0. Check it for yourself. So it is time to write g of x in its factorized form, and g of x is equal to x plus 1 times x minus 2 times x minus 3. And we use the factor theorem. If x is equal to minus 1, x is equal to 2, and x is equal to 3 are the zeros of a polynomial, then x minus minus 1, that is x plus 1, x minus 2, and x minus 3 will be the factors of the given polynomial. So the point minus 1, 0, 2, 0, and 3, 0 are the x-intercepts of this polynomial. The second step is determining its y-intercept, and the y-intercept of a polynomial is always make the first component 0 and take its constant term. The constant term of this is 6. So the point 0, 6 is where the graph of this polynomial crosses the vertical axis or the y-axis. Now the third step is determining the sign of g of x. And to determine the sign of g of x, first on a number line locate the 3 zeros of this polynomial, minus 1, 2, and 3. So order matters in this case. So the smallest of the 3 numbers will be on the left, and the larger of the 3 numbers will be on the right. So order delocating these 3 numbers on a number line. Here we have minus 2, minus 1, here we have 2, here we have 3, and right extreme is always positive infinity, left extreme is negative infinity, and the number of factors is 1, 2, and 3. So we have to prepare a table having 4 rows, 1, 2, 3, 4. The 3 rows are to determine the sign of the factors, and the last row is to determine the sign of the polynomial. So as we did for the previous example, let us start from the first factor of this polynomial, x plus 1. It is equal to 0 when x is equal to minus 1. Then we have to analyze what happens to the sign of x plus 1 when we assume a value less than minus 1 and a value greater than minus 1. For values less than minus 1, you can evaluate x plus 1 by substituting x with minus 2, minus 3, minus 4, minus 5, etc. For example, if you evaluate x plus 1 by substituting x with minus 2, minus 2 plus 1 is minus 1. If you substitute minus 3 plus 1 is minus 2. That means unless the interval is changed, x plus 1 remains less than 0 or negative for values less than minus 1. So we put this negative sign. Then for values greater than minus 1, for example, if you take x is equal to 2 and 3, 2 plus 1 is 3 and 3 is positive. 3 plus 1 is 4 and 4 is positive. That means for values greater than minus 1, x plus 1 is positive. Then consider the next factor of this polynomial, x minus 2. And x minus 2 is equal to 0 when x is equal to 2. And what happens to the sign of x minus 2 for values less than 2? You can evaluate, you can check and evaluate x minus 2 by making the value of x equal to minus 1. So minus 2 minus 1 is minus 3. Then for values less than 2. So we put this negative sign. Negative, negative to indicate that x minus 2 is less than 0 for values less than 2. And for values greater than 2, for example, if you evaluate x minus 2 at 3, 3 minus 2 is 1. If you evaluate at x is equal to 4, 4 minus 2 is 2, and 2 is positive. So we write this positive sign to indicate that x minus 2 is greater than 0 for values greater than 2. Now we consider the final factor of this polynomial x minus 3. It is exactly equal to 0 when x is equal to 3. And for values less than 3, for example, if you make the value of x minus 1 and 2, minus 1 minus 3 is minus 4, 2 minus 3 is minus 1. That means for values less than 3, x minus 3 is negative. So we write this negative sign to indicate that x minus 3 is less than 0 for values less than 3. Negative, negative, negative. And for values greater than 3, obviously, x minus 3 is positive. Now this polynomial x cubed minus 4x squared plus x plus 6 is the product of x plus 1, x minus 2, x minus 3. That means the sign of x cubed minus 4x plus 6 is the product of the signs of these three factors. Negative times negative, it is positive. Positive times negative is negative. So x cubed minus 4x squared plus x plus 6, or the graph of G, lays below the x-axis for values less than minus 1. Then between minus 1 and 2, the product of these signs, positive times negative times negative. Negative times negative is positive. Positive times positive is positive. And the implication of this for the graph of g of x is its graph lays above the x-axis between minus 1 and 2. Remember, before it is positive, it crosses the x-axis at x is equal to minus 1. Then between 2 and 3, as you can see, the sign of x plus 1 is positive, the sign of x minus 2 is positive, but the sign of x minus 3 is negative. So positive times positive is positive, positive times negative is negative. Now again, the implication of this for the graph of g of x is its graph lays below the x-axis between 2 and 3. And finally, for values greater than 3, positive times positive is positive. So for x greater than 3, this polynomial g of x, its graph stays above the x-axis. So taking these pointers onto the xy coordinate plane, at x is equal to minus 1, at x is equal to 2, and at x is equal to 3, the graph of g crosses the x-axis, and at y is equal to 6, its graph crosses the y-axis. And from the sign chart, the value of g of x is negative, or it stays below the x-axis for values less than minus 1. So after crossing the x-axis at minus 1, the graph of this looks like this one. And between minus 1 and where the graph of this crosses the y-axis, it remains positive. And this is the point. It starts to turn back. Then it crosses the y-axis
the x-axis at 2. Then there is a peak, I mean a valley. We don't know the exact value of x between 2 and 3 where this valley is obtained. But we know for sure that between 2 and 3, the graph of g of x has a valley. Then after forming this valley, it starts to rise. It touches the x-axis at 3, and after 3, the value of g of x is remaining positive. Now the other thing we have to notice when sketching the graph of a polynomial is the number of turning points. The peaks and the valleys on the graph of a polynomial are called the turning points. Now count the number of turning points. We have 1, 2. The degree of this polynomial is 3, and the maximum number of turning points the graph of a polynomial whose degree n can have is n minus 1. So if the degree of a polynomial is 3, then 3 minus 1 is 2. So the maximum number of turning points that the graph of this polynomial can have is 2. And actually, this polynomial has 2 turning points. A peak at x is equal to 0 and a valley between 2 and 3. These two, the peak and the valley, they are called turning points. And if you count them, they are 2. And they are in line with this important information I told you, that is the maximum number of turning points the graph of a given polynomial can have is n minus 1, where n is the degree of the given polynomial. I think these 4 examples are enough for today. If you have any question regarding these examples, you can forward it, or else this is all I have for today, and we will meet next Monday. Do you have any question?
No.
Yes, you can forward.
No. No, there is no.
ከሌለ የሚቀጥለው ሳምንት ሰኞ ዕለትም ይሄንን እንቀጥላለን። ግን የተሻለ የሚሆነው ይሄንን ግራፍ በቪዲዮ የተሳሉትን ብልክላችሁ ስለሚሆን የሚቀጥለው ሳምንት ላይ በግራፍ ላይ ቪዲዮ እልካለሁ። ግን ሰኞ ዕለት ይሄንኑ ተጨማሪ የፖሊኖሚያል ግራፎችን እየሳልን እዚሁ ላይ በዙም ዲስከስ እናደርግበታለን። ግን ይበልጥ ኮንሶሊዴትድ የሆነ ኢንፎርሜሽን እንዲኖራችሁ I will start sending a video starting from the coming week. Thank you and have a good weekend. Okay. Okay, good afternoon to you. If you remember the previous week, we have seen some examples on how we can sketch the graph of some polynomial functions. And we have said that sketching the graph of a function is a process, and this process involves some steps. And we have categorized the polynomials based on their degrees as a polynomial whose degree is 2. We have a previous experience how to sketch the graph of such a polynomial, because in grade 9 mathematics you have learned how to sketch the graph of a quadratic function. To sketch the graph of a quadratic function, the steps involved are determining the x-intercept, the y-intercept, the vertex, and nature of the parabola. After obtaining these 4 pointers, then we join these 4 pointers by a curve called parabola. And the nature of this parabola is of 2 kinds. upward or downward, and this is directly related to the sign of the leading coefficient. If the sign of the leading coefficient is a positive number, then we use an upward parabola to join these 4 points on the xy coordinate plane. And if the leading coefficient of this degree 2 polynomial is a negative number, then we use an upward parabola, an inverted U-shaped parabola, to connect these pointers to sketch the graph of a given degree 2 polynomial. On the other hand, if the degree of a polynomial is greater than or equal to 3, then the steps involved in sketching the graph of this polynomial has 3 steps. These 3 steps are: one is determining its x-intercept, then the second one is determining the y-intercept, but you all have to know that determining the y-intercept doesn't involve any calculation. Rather, you simply take its first component 0 and its second component, the constant term of the polynomial, because it is the point where the graph of the polynomial crosses the y-axis, and the pointers on the y-axis has first component 0 and second component -6. So this is the second step. And finally, to see how the graph of a given polynomial behaves, we construct a sign chart, and we observe the last row of the sign chart constructed to determine where the graph of this polynomial lays below the x-axis, where it lays above the x-axis. So for this case, we are going to see these 3 examples. The first one is a degree 3 polynomial, the second one is a degree 4 polynomial, and the third one is a degree 3 polynomial. So x-intercept is simply p of x is equal to 0, x cubed plus 2x squared minus 5x minus 6 equal to 0. Using the rational root test theorem, because the leading coefficient of this polynomial is 1, list the factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So if this polynomial has any rational 0, it must be from among this list of 8 numbers, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. But you have to be careful, because when a polynomial has degree an odd number, then it necessarily crosses the x-axis at least once. Therefore, if you cannot find a 0 using the rational root test theorem, then you have to try to get at least 1 0 using location theorem, because location theorem is used to determine where f changes its sign between consecutive integer, there is at least 1 irrational 0 of the polynomial. So using that fact, you can get the correct graph of the given polynomial. So for this case, x cubed to x squared minus 5x minus 6 equal to 0. Now you have to try minus 1 and 1, minus 2 and 2, minus 3 and 3, minus 6 and 6. So from among the list of these 8 numbers, you can check it for yourself: 2, minus 3, and minus 1. From among these 8 numbers, these 3 numbers does make the polynomial equal to 0. So we write this polynomial in factorized form: x plus 1 times x plus 3 times x minus 2 equal to 0. But if you are really interested in getting each of these zeros, going through the steps, then at least you can start from the simplest rational zeros of the possible simplest rational zeros of this polynomial. That means plus or minus 1. So because minus 1 makes this polynomial equal to 0, then x cubed to x squared minus 5x minus 6 will be divided to x plus 1. Then, because x plus 1 is a factor of this, obviously the remainder is 0. So you factorize the quotient, and the quotient is a degree 2 or a quadratic expression. You know how to factorize, or how to factorize a degree 2 polynomial or a quadratic expression? You can at least use the general quadratic formula and obtain the other factors as x plus 3 and x minus 2. So without the need to waste our time on that. Simply x cubed to x squared minus 5x minus 6 can be obtained from the product of x plus 1, x plus 3, and x minus 2. If this is the case, then x plus 1 equal to 0. It gives us x is equal to minus 1. X plus 3 equal to 0. It gives us x is equal to minus 3. X minus 2 equal to 0. X is equal to 2. Now from this, the pointers minus 1, 0, minus 3, 0, and 2, 0 are the x-intercepts of this polynomial P. That means these 3 pointers are the pointers where the graph of P of x crosses the x-axis. So their second components are equal to 0 because a point belongs to the x-axis if its second component is equal to 0. Because the constant term of this polynomial is minus 6, 0, minus 6 is its y-intercept, a point on the y-axis. Actually, there are a list of general properties of polynomials which I am going to mention for you later in our discussion. From among these general properties of graphs of a polynomial, one is the graph of every polynomial crosses the y-axis and only once. No polynomial, or there is no polynomial function whose graph can cross the y-axis more than once. But in the case of the x-axis, it may cross once, twice, 3 times, 4 times, in general n times, or it may not at all cross the x-axis. So if we obtain the y-intercept, the next step is constructing a sign chart to determine where the graph of P of x lays below the x-axis and where it lays above the x-axis. So to construct the sign chart, use these 3 numbers which are the zeros of the polynomial, minus 1, minus 3, and 2. Then orderly locate them on a number line. Because from these 3 numbers, minus 3 is the smallest. On the left extreme, there will be minus 3, then minus 1, and right extreme is 2. That means minus 3, minus 1, 2. And as I told you last time, if you continue writing other numbers to the right of 2, then a very large positive number which is represented by positive infinity, a very small number represented by negative infinity. Now the interval from negative infinity up to infinity, it is simply equal to this set, the set of real number, and the interval from negative infinity up to positive infinity are the same, or they are equal. Now consider the 3 factors of this polynomial: x plus 1, x minus 2, x plus 3. Don't bother about which one must come first, then which one must be written after which factor of this polynomial. It doesn't matter. You have to write the factor you wish to write first. If you want to write x minus 2 first, then you can write x minus 2, then x plus 1, x plus 3, or you may start from x plus 3. It doesn't bring any change on the sign of the polynomial. Rather, we have to focus on what is the sign of x plus 1, because x plus 1 is equal to 0 when x is equal to minus 1. So x is the sign of x plus 1 negative or positive for values less than minus 1 and greater than minus 1. For example, for values minus 1, for example, you can take minus 3. So if you substitute x by minus 3 plus 1 is negative. It means the sign of x plus 1 is negative or less than 0 for values less than minus 1. So here we write negative, negative to indicate that x plus 1 is less than 0 for values less than minus 1. Now, for values greater than minus 1, for example, if you take this number 2, 2 plus 1 is 3. If you substitute 3, 3 plus 1 is 4. If you substitute 4, 4 plus 1 is 5. So there is no need to take so many numbers to know the sign of x plus 1. Rather, take one integer that is greater than the given 0 of the factor and less than the given factor of that, the given 0 of that factor. Then you can test and determine its sign. So if at x is equal to 2, x plus 1 is positive, then in this interval minus 1 up to positive infinity, it remains positive. Actually, it is positive. So beyond minus 1, that is for values greater than minus 1, x plus 1 is positive. Then pass to the next factor, x minus 2. Obviously, x minus 2 is equal to 0 when x is equal to 2. So at x is equal to 2, you write this to indicate that the value of x minus 2 is 0. Now for values less than 2, you can either test x minus 2 at x is equal to minus 1 or at x is equal to minus 3 or any other integer less than minus 1. I mean positive 2. So for example, at minus 1 minus 2 is minus 3. That means the sign of x minus 2 for values less than 2 is negative. So you write negative, negative, negative to indicate that x minus 2 remains negative below or for values less than 2. Next, we determine the sign of x plus 3. X plus 3, it is equal to 0 when x is equal to minus 3. So we write at x is equal to minus 3, x plus 3 is 0, and for values less than minus 3. For values less than minus 3, for example, you can take minus 4, minus 5, etc. Minus 4 plus 3 is minus 1, minus 5 plus 3 is minus 2. That means the sign of x plus 3 is negative for values less than minus 3, and it is positive for values greater than minus 3. Now, what is the sign of p of x? Remember, p of x is equal to x cubed plus 2x squared minus 5x minus 6, which is equal to the product of x plus 1, x minus 2, x plus 3. Now take the product of the signs of these three factors. Negative times negative is positive, positive times negative is negative. Therefore, the graph of p of x stays below the x-axis for values less than minus 3. Then, as you can see here, p of x touches the x-axis. So, when you are observing the last row of the table at the values where we write 0, it means the graph of that polynomial touches the x-axis at that value. Then, between minus 3 and minus 1, take the sign of the product of these factors as the sign of p of x. Negative times negative is positive, positive times positive is positive. Therefore, the graph of p of x lays above the x-axis between minus 3 and minus 1, and it again comes back and touches the x-axis at x is equal to minus 1. Then positive times positive, it gives you negative. That means the graph of p of x lays or stays below the x-axis between minus 1 and 2. And finally, x plus 1, x minus 2, and x plus 3, because they are positive, for values greater than 2, p of x, its graph stays above the x-axis for values greater than 2. Now, when you are sketching the graph, you have to mark these 4 points. It is a must. Minus 3, minus 1, and 2 on the x-axis or on the horizontal axis to indicate where this function crosses the x-axis, and minus 6 on the y-axis or the vertical axis to indicate where the graph of this polynomial touches the y-axis. So then you have to interpret this table. We already interpret this table. Therefore, after crossing the x-axis at minus 3, the graph of p of x stays below the x-axis, means you have to sketch this. Then at x is equal to minus 3, it crosses the x-axis. Then it goes up between minus 3 and minus 1. Then after reaching some point, it turns back because it must cross the x-axis at what? At x is equal to minus 1. So without bothering where the graph of this function turns or this peak appears, simply you have to turn back, and the graph of this polynomial crosses the x-axis at x is equal to minus 1. Then what happens to the graph of p of x? It will be clearly, or it can be clearly seen from the last row of this table. It comes back and it lays below the x-axis between minus 1 and 2. That means between minus 1 and 2, it is negative. But in this interval, it must cross the y-axis. So it crosses the y-axis at x is equal to, at y is equal to minus 6. Then it should return back up because at x is equal to 2, it must cross the x-axis, and beyond 2, it must be positive. So it starts to rise, it crosses the x-axis at 2, then after this, it is rising. Therefore, this is the graph of this polynomial p of x. And as I told you last Friday, the peaks and the valleys. There is one peak, there is one valley on the graph of P of X. These peaks and valleys are called local extremum. And I told you that a local extremum is a maximum or a minimum value of a function in a given interval, not in the whole set of the domain of that function. So, for example, if you see this peak is obtained between the values x is equal to -3 and x is equal to -1. We don't know where exactly it appears, but we can for sure tell that this peak is appearing between -3 and -1, and it is called a local maxima. Again, there is this value, and this value is occurred between the values x is equal to -1 and x is equal to 2. Actually, in this case, we know where exactly this value is occurring. At x is equal to 0, the value of y is -6, so it is a local minima. But these 2 points collectively, they are called local extremum points. And the other thing you have to remember, for the graph of a given n-degree polynomial, the maximum number of turning points, if its degree is n-1. So in this case, this polynomial has its degree 3. 3 minus 1 is 2. So the maximum number of turning points for the graph of this polynomial is 2. Actually, if you count them, they are 2. Turning point means the peaks and the valleys on the graph of a polynomial. They are called turning points, or they are local extremum points for the graph of a given polynomial. So this is the graph of P of X. We are done. If you have any question regarding how we can sketch or anything in the process of sketching the graph of this, you can forward it. If you don't have any question, then we pass to the next polynomial. Do you have any question?
No.
Okay. The next example is a degree 4 polynomial. But if you consider the terms of this polynomial, all of them contain x. Here x to the power of 4, x squared, x. So when you are determining its x-intercept, first factorize this. So when you are factorizing this, take out x. So you will be left with x cubed minus 19x plus 30. So x-intercept, x to the power of 4 minus 19x squared plus 30x equal to 0. X times x squared minus 19x. No, this is x cubed. Sorry, this is x cubed. So x cubed minus 19x plus 30 equal to 0. Now, already we obtained one of the factors of this polynomial. So the next step is factorizing x cubed minus 19x plus 30. Again, in this case, the leading coefficient of this polynomial is 1. List the factors of 30. The possible rational zeros of this polynomial are the list of the set containing the list of factors of 30. They are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 50, and plus or minus 30. So if this polynomial has any rational zero, it must be from among these numbers. Actually, I'm not going to waste on which one does make this 0. You can check this for yourself at home. Simply at x is equal to minus 5, x is equal to 3, and x is equal to 2. From this list of possible rational zeros of the polynomial does make this equal to 0. So the rational zeros of this polynomial are minus 5, 3, 2, and already we have obtained x is equal to 0. So this is a degree 4 polynomial, and a degree 4 polynomial can have 4 different zeros or 4 different factors at maximum, and any integer less than 4 can be a possible 0 or a possible number of factors of this polynomial. We actually obtain 4 different zeros. That means the graph of this polynomial touches the x-axis at 4 different points: minus 5, 0, 3, 0, 2, 0, and the origin. Because if you make the value of x equal to 0, then obviously, as you can see in this function, the constant term of this is 0. So there is x, we make it 0, this is 0, this is 0. So the graph of this function passes through the origin. So here we write the y-intercept as the point 0, 0. Then the next step is to see the sign of p of x in different intervals, construct a sign chart. And to construct the sign chart, consider these factors: x, x plus 5, x minus 3, x minus 2. And the numbers that makes this equal to 0 are 0, minus 5, 3, and 2. As we did for the previous example, locate these four numbers on a number line. So the smallest of this is on the left extreme, that is minus 5. Then orderly 0, 2, 3. The largest of these four numbers, it will be on the right extreme. And right extreme, a very large positive number, positive infinity. Left extreme, a very small negative number, negative infinity. Then write all these four factors: x, x minus 2, x minus 3, x plus 5. As I said earlier, the order which you follow to write these factors doesn't have any effect on the answer. So you can start from x, or you can start from x minus 2, x minus 3, x plus 5. Now, after writing these factors, then determine the sign of all the four factors. X is equal to 0 when it is equal to 0. X minus 2, it is equal to 0 when x is equal to 2. X minus 3 when x is equal to 3. X plus 5 when x is equal to minus 5. And the polynomial x power 4 minus 19x minus 19x squared plus 30x, it is equal to 0 when x is equal to minus 5, 0, 2, and 3. So we write at x is equal to minus 5, 0, 2, and 3, 0, 0, 0, 0, to indicate that the graph of this function crosses the x-axis at these four different points. Then, by taking the product of the signs of these factors, as you can see, for values less than or minus 5, this polynomial, its graph stays above the x-axis, between minus 5 and 0, below the x-axis, and between 0 and 2, above the x-axis, between 2 and 3, below the x-axis, above 3 or greater than 3, above the x-axis. So taking this onto the xy coordinate plane, you can obtain the graph of this polynomial as follows. As we have said, you have to mark these 4 or 5 points on the xy coordinate plane. It is a must. So minus 5, 0, origin 0, 0, 2, 0, 3, 0. Because the graph of this function crosses the y-axis at the origin. So we mark the other point at the origin. Then you have to completely depend on the last row of this table. For values greater than, less than minus 5, the graph of this polynomial is positive. That means it is rising and it stays above the x-axis. That means when the value of x is minus 6, minus 7, minus 8, minus 9, minus 10, as you can see, the graph of this is rising and above the x-axis. And when x is equal to minus 5, because it is one of the zeros of this polynomial, so it touches the x-axis. Then from the sign chart we constructed, between minus 5 and 0, the graph of this polynomial is negative. That means it lays below the x-axis. So it lays below the x-axis, but because it should return back and touch the origin, so somewhere there must be a valley. So it starts to rise, then it touches the origin. Then what happens to the graph of this polynomial after the origin? Let us return back and observe the last row of this table. Between 0 and 2, where 0 and 2 are the two rational zeros of this polynomial, the graph of this polynomial is positive and rising. But remember, after crossing the origin and after rising, it should form a peak and should return back to the x-axis to cross it at x is equal to 2. So it forms a peak, it returns back, it touches the x-axis at 2, then what happens to the graph of p of x? Again, we return back to the sign chart. So between 2 and 3, the graph of this polynomial is negative, means it stays below the x-axis, it forms a valley, then after forming this valley, it should return back to the x-axis and it must cross it at x is equal to 3. That means it forms this valley, returns back up, it crosses the x-axis at 3. Then, as you can see from the sign chart we construct, after x is equal to 3, or for values greater than 3, the graph of this is positive, means positive and rising. Now count the number of peaks and valleys on the graph of this polynomial. There is 1 valley and 2 peaks. So these peaks and valleys are the turning points. So if you count them, 1, 2, and 3. The graph of this polynomial p of x has 3 turning points, and it is the maximum, because the maximum number of turning points the graph of a given polynomial can have is obtained by subtracting 1 from its degree. So the degree of this polynomial is 4. 4 minus 1 is equal to 3. So 3 turning points, and from these 3 turning points, 2 are valleys. Therefore, the graph of this polynomial has a local minima at these 2 points, and there is 1 peak, and at this peak, the graph of this polynomial has a local maxima. Now, if you have any question, you can forward it, or else we pass to the next example. Do you have any question? ያው እንደተለመደው አንድ ስም ነው መጥራት ብዙ ጊዜ የሚቻለውና ሮብሰን ሌሎቻችሁ ስጠራም መልስ ስለማሰጡኝ ሮብሰን
የለም ሚስተር
ልቀጥል እሺ Okay, we are on the third example. The leading coefficient of this polynomial actually is negative, but it is a degree 3 polynomial, as we did for the first example, or the examples we did consider on Friday. The first step for a polynomial whose degree is greater than or equal to 3 is determining its x-intercept. So again, this is very fortunate. The leading coefficient of this polynomial is again -1. So we need to list out the factors of the constant term. The constant term in this case is 20, and its factors are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. So if this polynomial has any rational zero, it must be from among these numbers. Now you have to try for yourself, but at x is equal to 5, x is equal to -2, and x is equal to 2, this polynomial is equal to 0. So take this negative sign as a common factor. So you have x minus 5 times x plus 2 times x minus 2 equal to 0. Now x minus 5 equal to 0, it produces x is equal to 5. X plus 2 equal to 0, x is equal to -2. X minus 2 equal to 0, x is equal to 2. Now from this last step, we can conclude that the points -2, 0, 2, 0, and 5, 0 are the x-intercepts of this polynomial f. Then the y-intercept is simply obtained by making the value of x equal to 0, but there is no need to make any calculation. Simply take the first component of the point 0 and take the constant term, that is -20. Now, when you are sketching the graph of this polynomial, you have to mark these 4 points on the xy coordinate plane. It is a must. You can't omit one of these points. You have to mark points on the x and y axis, these 4 points. Then you can depend on the sign chart constructed, and then you can sketch the graph as follows. The next step is obtaining the sign of this polynomial. So to see the sign of p of x in different intervals, construct a sign chart. So to construct the sign chart, we consider all the factors of this polynomial, namely x plus 2, x minus 2, x minus 5. Then these three factors of the polynomial are equal to 0 at x is equal to minus 2, 2, and 5. So x plus 2, it is equal to 0 when x is equal to minus 2, x minus 2 when x is equal to 2, x minus 5 when x is equal to 5. Don't forget to write the rational zeros of this polynomial order. Order matters. You cannot write these rational zeros of the polynomial as you wish, as it is true for these factors. We can write the factors beginning from any of the factors. You can begin from x plus 2, x minus 2, x minus 5. But here, it is not possible. We have to write orderly. Order matters. So after marking this, then x plus 2 for values less than minus 2 is negative, and for values greater than minus 2 positive. X minus 2 for values less than 2 is negative, for values greater than 2 is positive. X minus 5 for values less than 5 is negative, and for values greater than 5 is positive. Then the sign of this polynomial. Actually, in this case, you have to be careful because this polynomial is given as negative x minus 5 times x plus 2 times x minus 2. So after taking the product of the signs of x minus 5, x plus 2, and x minus 2, we have to multiply this by negative. So in general, what is obtained from this table is the sign of this polynomial is positive for values less than minus 2, between minus 2 and 2, negative, between 2 and 5, positive. For values greater than 5, it is negative. Don't forget this. A very large positive number represented by positive infinity, a very small negative number represented by negative infinity. Now we can sketch the graph of this polynomial. And remember from the information I gave you earlier, the 4 pointers, the pointers where the graph of this polynomial crosses the x-axis and the y-axis, it is a must to mark them on the xy coordinate plane. These pointers are minus 2, 0, 2, 0, 5, 0, and its y-intercept is 0, minus 20. So we totally depend on the last row of this table. I told you earlier how to interpret this. For values less than minus 2, as you can see, the graph of this polynomial is positive and rising. That means when the value of x is minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, the graph of this is, it stays above the x-axis and rising. So you have to sketch this part of the graph. Then, as you can see from the last row of this table, the graph of this polynomial must return back and touch the x-axis at x is equal to minus 2. So it was rising, but at x is equal to minus 2, it is equal to 0. Then between minus 2 and 2, remember 2 is the other point where the graph of this polynomial crosses the x-axis. The graph of this polynomial is negative. Remember, it should form a valley before returning back and touches the x-axis at x is equal to 2. So the point where the graph of this polynomial touches the y-axis is at minus 2, minus 20, sorry. So it forms the valley at x is equal to 0 or y is equal to minus 20. Then it starts to rise and touches the x-axis at x is equal to 2. So what happens to the graph of this polynomial after it touches the x-axis at x is equal to 2? Then observe the last row of the table. Between 2 and 5, where 5 is the other point where the graph of this polynomial touches the x-axis. The graph of this is positive and rising, but it can't stay positive and rising because it should return back and touch the x-axis at x is equal to 5. Therefore, it forms a peak, it returns back, it touches the x-axis at x is equal to 5. Then what happens to the graph of this? As you can see, its graph never returns back up. Rather, it is falling for values less than 5. So count the number of turning points. 1, 2. The degree of this polynomial is it 3 or 4? The degree of this is 3. Therefore, it can have 2, 1. Oh, here, this is by mistake, minus x. So negative of x minus 2, x minus 5, x plus 2. There is no need to write x. So the graph of this polynomial is, it looks like this one. And we're done. We sketch the graph of this polynomial. Now, our discussion next must focus on the general properties of a polynomial. There are a list of 7 general properties of a polynomial function. The first property of graph of a polynomial function is given, and as you can read from your screens, the graph of polynomial functions are continuous curves. These properties are true for all polynomials. So the graphs of polynomial functions are continuous curves. What does it mean? Continuous curves means they have no gaps and sharp corner. What does it mean? For example, if you sketch the graph of a polynomial like this, for example, then maybe now this cannot be a graph of a polynomial. The reason is, now you are in grade 10, and after grade 10 mathematics, and including in grade 10, we will be learning about discontinuous functions. Discontinuous, a function, or we know whether a given function is continuous or discontinuous throughout its domain. If its graph is given, from the graph, we have to search for such a point. If there is a hole like this indicates in mathematics on the graph of a function that the function is discontinuous at this point. There is a hole or holes on the graph of a given function in mathematics, that implies the function is discontinuous, or there is a value or values where the function is undefined. Therefore, this cannot be the graph of a polynomial. Another case is sharp corner. For example, if someone draws the graph of a polynomial like this, again, this cannot be the graph of a polynomial because here is a sharp corner. This is V-shaped, but the graph of a polynomial is a curve. It looks like a wave, smooth, continuous curve. So the peaks and the valleys they have a shape U or inverted U shape. So this cannot be the graph of a polynomial. This cannot be a graph of a polynomial. So the first point is the graphs of polynomial functions are continuous curves. That is, they have no gaps and sharp corners. The second one is for very large positive values of x. That means as x approaches to positive infinity. When I was constructing the sign chart to know where the given polynomial, its graph stays below the x-axis, where its graph stays above the x-axis earlier, we denote, or we use this symbol to represent a positive, a very large positive number, a negative number, a very small negative number. So for very large positive values of x, that is as x approaches to positive infinity, and for very large negative values of x, x approaches to negative infinity, the value of y approximately equals the value of the leading term, or the functional value of the polynomial is solely determined by the leading term. The other terms of a polynomial may have an effect, but they lose their effect after some point. And this explanation simply tells you that beyond some value to the right of the origin and to the left of the origin, the functional value of a polynomial theta totally is determined by its leading term. The leading term is the term where maximum exponent or maximum power of x is observed. So by considering the sign of the leading term, you can determine what happens to the graph of that polynomial to the left and to the right of the origin. And the third one is the peaks and valleys on the graph of a polynomial function represent local extremum. A local extremum refers to a local minima if the graph of a polynomial forms a peak at that point, or a valley, that is a local minima if the graph of a given polynomial forms a valley at that point. So local extremum in general, it is a collective name to the peaks and valleys appearing or observed on the graph of a polynomial. The fourth one is the graph of any polynomial function crosses the y-axis only once. There is no polynomial function whose graph crosses the y-axis more than once. So this is the fourth general property of graph of a polynomial function. The fifth one is the graph of every odd degree polynomial is rising on one extreme and falling on the other. The graph of every odd degree polynomial, for example, we can consider the third example. As you can see, it is rising on the left extreme because as the value of x is a very small number, or as x approaches to negative infinity, this is rising. Because this is an odd degree polynomial, then as x is a very large positive number, it is falling. You can observe from here, the graph of this polynomial is falling as x is larger and larger. So the graph of every odd degree polynomial is rising on one extreme and falling on the other. The sixth and the seventh are the graph of every even degree polynomial is rising or falling on both extremes. For example, you can take the graph of the second polynomial. It is 8 degree 4, x to the power of 4. Example B means x to the power of 4 minus 19x squared plus 30x. So this is an even degree polynomial. Now, if you see on both extremes, as x gets closer to negative infinity, the graph of this is rising. As x is closer to positive infinity, or it is becoming a very large number, again on this direction, it is rising. So for an even degree function, if it is increasing on one extreme, then it is rising or increasing on the other. If it is falling, then it must be falling on the other extreme. And the final point for the day, the sign of the constant term tells where the graph of a polynomial crosses the y-axis. If the constant term of a polynomial is a negative number, then its graph crosses the y-axis below the origin. And if the constant term of a polynomial is a positive number, its graph crosses the y-axis above the origin. And if the constant term is equal to 0, then the graph of the given polynomial passes through the origin. That is what the seventh general property of a polynomial explains. This is all I have for today. As I promised last week, the coming Thursday or Friday, I will try to send you a video, and we will see additional examples the coming Friday. Till that, thank you for your listening. See you on Friday. What's the thing?
ወደ አራት ቀንሷል። እንደምን አደራችሁ? እንተ ጀምር ያለው ክላስ ጓደኞቻችሁ አልሰሙ ሆነው ነው ወይስ ምንድን ነው? አንድ ሰው የሚመልስልኝ? ሄሎ፣ የምታውቁት የተለየ ነገር ካለ እንድትነግሩኝ ነው።
አይ ሚስተር አናውቅም።
ሩት ምንም አታውቁም?
አዎ
ኦኬ። Okay, let us begin our discussion. In the meantime, if there are students who joined us, I will let them to attend this class. But let us begin our discussion with the first example. The first example is draw the graph of the polynomial function f of x is equal to x squared times x plus 1. Actually, to sketch the graph of such a polynomial, it is simple because already the polynomial is given in its factorized form. So the first step, that is determining the x-intercept of this function, is simple because you set these factors equal to 0 and you can determine the x-intercept or the point where the graph of this polynomial touch or cross the x-axis. So in this case, set x squared equal to 0, x plus 1 equal to 0, x minus 2 equal to 0. This one, x is equal to 0, x plus 1 equal to 0, x is equal to minus 1 is obtained. From x minus 2 is equal to 0, x is equal to 2 is obtained. Therefore, the graph of this polynomial cross or touch the x-axis at 3 different points. These points are minus 1, 0, 2, 0, and the origin, whose first and second components are 0. Actually, if a given polynomial is given in factorized form, and if x with any power is a factor of this polynomial, then the graph of this polynomial passes through the origin. So there is no need to determine the y-intercept, because this point, the origin, is a common point for the x-axis and the y-axis. And if you remember, those common properties of polynomial function I told you last time, one of them is the graph of every polynomial function crosses the y-axis only once. So there is no need to find the y-intercept. Already the origin, this point minus 1, 0 and 2, 0 are the intercepts of this function. Now, to correctly sketch the graph of this polynomial f of x, the next step must be determining where the graph of f of x lays below the x-axis and where its graph lays above the x-axis. And this is possible by constructing a sign chart. And to construct a sign chart, you have to take the zeros of the given polynomial. These are 0, minus 1, and 2. Then orderly locate these three numbers on a number line. So the smallest of these three numbers, minus 1, left extreme, then 0, then 2, the largest of the three numbers on the right extreme. And here always a very positive number, horizontal positive infinity. Then write the factors starting from any one, x. Then if you have the sign of x, you can determine the sign of x squared. Then take the next factor, x plus 1. But to determine the sign of x minus 2 to the power of 4, we have to first determine the sign of x minus 2. So take x minus 2, then x minus 2 to the power of 4. Then finally, the last row of this table shows the sign of f of x. And to determine the sign of f of x, we have to take the product of the signs
x squared, x plus 1, and x minus 2 to the power of 4. So x, it is equal to 0 when x is equal to 0, and for values less than 0, the sign of x is negative. So you have to write this sign to indicate that the sign of this is negative. And for values greater than 0, this is positive. Then x squared. Take the sign of x and square it. Negative square is positive. Negative square is positive. 0 square is 0. Positive square is positive. So the sign of x square is, except at x is equal to 0, everywhere it is positive. Now the next factor, x plus 1, it is equal to 0 when x is equal to -1. And useless, the sign of x is negative. And for minus 1, the sign of x is positive or greater than. It is equal to 0 when x is equal to 2. And for values less than 2, x minus 2 is negative, and greater than 2, x minus 2 is positive. Now, x minus 2 the power of, remember here, negative number raised to an even exponent is positive. You obviously know that a positive number raised to an even exponent or an odd exponent, it always produces a positive number. So x minus 2 to the power of 4 at x is equal to 2 is 0, except at x is equal to 2, everywhere raised to, I mean a negative number raised to an even exponent, it produces a positive number, positive, positive, a positive number raised to even or odd exponent, it doesn't matter, it produces a positive number. Therefore, the sign of x minus 2 to the power is positive everywhere, and at x is equal to 2 is 0. The sign of f of x in this 1, 2, 3, 4 different intervals. Now take the product of the signs of x squared, x plus 1, x minus 2 to the power of 4. So for values less than -1, positive times negative times positive. Positive times negative is negative. Negative times positive is negative. Therefore, f of x, its graph lays below the x-axis for values less than -1. Then between -1 and 0, take the product of the sign of x squared, which is positive, the sign of x plus 1 positive, the sign of x minus 2 to the power of 4 positive. So the product of 3 positive quantities produce a positive number. So the graph of f of x between -1 and 0 lays above the x-axis. Then between 0 and 2, between 0 and 2, take the product of x, the sign of x squared, x plus 1, x minus 2 to the power of 4 to determine the sign of f of x. So positive times positive times positive, again it is positive. So in general, between -1 and 2, the graph of f of x lays completely above the x-axis. Now what is left is the sign of f of x for values greater than 2. So take the product of the sign of x squared, which is positive, x plus 1 positive, x minus 2 to the power of 4, it is positive. So the product of three positive quantities, it produces a positive quantity. Now we know what f of x graph lays below its graph crossing the x is -1, is 0. This formation with a smooth curve, we can sketch the graph of this polynomial. You have to mark on the xy coordinate plane the point which the graph of f of x crosses the x and the y-axis. Therefore, -1, 0, 2. Then completely you can depend on the last row of the same chart to sketch the graph of this polynomial. Now for values less than -1, the graph of f of x negative